All right, what's going on, everybody? Today we're doing another LeetCode problem. This one's called Invert Binary Tree. So they basically give us the root of a binary tree. They want us to invert the tree and then return the root. So we're going to be basically swapping all of the nodes in place and then returning the root of a binary tree that they give us. So that's pretty much the extent of the problem statement. Just to reiterate that, maybe explain it in a little bit of a different way if that doesn't resonate. So we're basically mirroring all of the nodes. They want us to reorganize all of the pointers such that the binary tree is mirrored along a mirror line that's on the y-axis. So for this example 1, we can see this node with the value 1 is going to move from the bottom left of the tree all the way to the bottom right of the tree, or the bottom left leaf node is going to become the bottom right leaf node. So let's get into the problem. There's a couple ways you can do this. You can do it recursively. I'm going to do it iteratively just so we can avoid any issues with memory overflow in the recursive call stack. Because that, if you have smaller trees and a lot of compute, you probably won't run into memory overflows in terms of space on the recursive call stack, but it isn't exactly a guarantee, so I am going to do this iteratively with a stack. So for algorithm, we know we have to at least look at each node in the tree also. So this is going to have to be linear time complexity with respect to how many nodes there are in total in the tree. And then for space complexity, we're also going to have linear space complexity because we're going to use a stack basically to make sure we're swapping each node. So let's just pretend we have a stack over here, and that's a little low. Do it there. Okay, so let's pretend we have a stack here. So before we start looping, we're gonna push the root node to our stack for our algorithm. So our root node is now in our stack. Okay, now we're gonna start looping, and we're gonna loop. We're just gonna do a while loop while our stack has elements. So, or in other words, while our stack size is greater than 0, or while our stack is not empty. That's all synonymous. So while our stack is not empty, we're gonna pop that first node. We're gonna get a pointer to it, and we're gonna pop it, and we're gonna push its children nodes to the stack. So in this case, it's gonna be the children nodes. We have a pointer to it 2 and a pointer to this node that's labeled by the 3. So let's push those to our stack. So 2, 3, and then what we want to do is we want to basically use a temporary node pointer to help us swap these nodes, or you could use the built-in swap function, but we're just swapping the pointers to these nodes at our at the parent node, right? So the left child would become the right child, and the right child would become the left child. So this is really going to be done in place, but just so we can compare with the original input, I'm going to reconstruct it over here. So that 3 is going to be there, and then the 2 will be here, and obviously all of the children are going to come with it. So I'll also illustrate that. So that's what the tree is going to look like at this point of the algorithm. And this is the left child here, this 4 left child of the 2. Okay, so then that's one iteration. So we're going to go again to the top of the stack. We're going to pop this 3, get a pointer to it, and we're going to push its children. So its children are the 5 and the 6. So just pushing those onto the stack, and then we want to swap those. So swapping those nodes, the 6 will be over on the left child of the 3, and then the 5 will move to the right child of the 3. Okay, so that's another iteration. Now we want to go back to the top of the stack. We're going to pop this 6, we're going to add its children, and it doesn't matter if the children are null. We're still going to push them to the stack, because notice we're going to get to this edge case here where we have a 4 on the left child and then a null pointer on the right child. We still need to swap that null pointer with the potential non-null node, right? So the way I'm going to implement this algorithm is we're still going to push null pointers to the stack. So the 6 is going to have 2 children left and right, and both are going to be null. So that'll be null, null. Okay, and now we can push or get this. So that's another iteration. We're going to go back to the top of the stack. We don't have to push. So we're going to do an if statement on every node before we push children to the stack, right? Because obviously this null pointer isn't going to have any null pointers or any children at all to push. So we're not going to do anything there. Okay, so top of the stack again, same thing. We don't have to do anything because it's a null pointer. So at this point, top of the stack will be our 5. That has 2 null pointer children. So let's push those to the stack, pop them because we don't have to do anything. And then this, so now we're at this 2. We're going to push both of its children. It's got a 4. It's got a node there, and then it's got a null pointer on the right side. So back to the top of the stack. Don't have to do anything for the null pointer. And then this 4, we need to push its children. Oh, and by the way, we need to swap those, right? So at this point, actually, before we would go to the next iteration, we were just at the 2, we pushed the 4 and a null pointer to the stack. Now we need to swap those. So the 4 is just going to end up on the right side. Okay, so now we're going to go. So that's it for that iteration. Go to the top of the stack, don't have to do anything. For this 4, we have to add the null pointer children. So add those. Okay, that's another iteration. Okay, now we're gonna pop top of the stack. Don't have to do anything because it's null. Pop top of the stack, don't have to do anything because it's null. At this point, we're done because I forgot to cross out this 2 earlier, but at that point we'll have looked at every node in the tree, and our tree should be perfectly inverted, so we can just visually verify that here. And we would return obviously that root, or the pointer to the root node. So just to reiterate on the time and space for this, the time is going to be big O of n with respect to the total number of nodes in the binary tree. Obviously, like if we were being really pedantic about how many steps it takes, it would be more than just the number of nodes in the tree, right? It's every node and it's potentially null pointer children, right? So technically, the number of steps that it will take to execute is going to be greater than the number of nodes in the stack. It's going to be the number of nodes in the stack and all of their children. So, but of course that simplifies to linear. So linear time and then linear space, also same idea there, because we need to store every node and its children in the stack. So that's pretty much it for the algorithm. So let's go ahead and code this up now. So the first thing we want is a stack of tree node pointers. I'll just call that st. And we also want to push the root node into that stack at first. So we'll push that root. And we want some pointer variables. So I'll make a pointer variable for each node that we pop at the top of the stack. So I'll just call that n. And we'll just assign that to null pointer to avoid unpredictable behavior. Tree node star. We also want a temporary pointer to help us swap nodes. And you can also like declare these within the while loop, but what happens with scope, those variables are gonna like basically be re-declared every time the loop executes, which is like a little more inefficient than declaring them out here like this. So So we're gonna say while stack is not empty, right? And we push that root node, so as long as that's not null, this block of code will be reached. It'll run at least until we exhaust all the nodes in our tree. So so the first thing we want to do is get a pointer to that top node in the stack. So you can say stack.top. Now that we have a pointer to it, we're done with it in the stack, so we can just pop it. And then you want to check that make sure it's not a null pointer before we start doing stuff with the children, right? So, because remember, we didn't have to do anything with null pointers in the stack. So we're gonna make sure that is there's an actual node there. So if node, we're going to push both children to the stack. So we're gonna push the pointer to the left child node and the pointer to the right child node. And then we can just swap those, right? So we need to store the pointer to the left node temporarily, and we can assign it to the pointer to the right node. And then finally, we can set the right node back to that temporary pointer that we stored. So at that point, the nodes will be swapped, and it's going to do that all the way down the tree, top down. So once this while loop is done executing, we just need to return the root node. That's pretty much it for the algorithm. So let's go ahead and run that. So yeah, hopefully this video helped you understand the algorithm better for the iterative solution for this. If it did, leave a like and subscribe, and I'll see you guys in the next piece.